Dear students, in this class we are going to study about rectifiers. Basically, rectifier is a device that converts AC supply into DC using diodes. Rectification can be done by half-wave or full-wave rectifier circuit. This full-wave rectifier circuit further be classified as center tap or bridge rectifier. We will see one by one. First, we are going to discuss about the half-wave rectifier. This is the circuit of half-wave rectifier where it consists of one transformer having N1 and N2 term and a diode D and a load resistance RL. This transformer is used for stepping down the supply voltage. Basically, we have AC supply, AC input here, which is normally 230 volt 50 hertz in case of our country. We have to stepping down this supply voltage to a level of diode voltage, which is about 24 volt or 12 volt, and load resistance is used as a load which need DC supply, where you are applying this sinusoidal AC input at this point and we get reduced sinusoidal voltage at between point AB. During positive half cycle, the diode will be forward bias. We can see from this figure, this is point A and this is point B. During forward bias, we have a voltage like this. This will appear at point A. That is, if point A will be positive and point B will be negative. And at this condition, the diode will be forward bias. For ideal diode, we take under forward bias condition, it behaves like closed circuit, closed switch. Then the applied voltage here will appear, go through the resistance, load resistance RL, and during positive half cycle, the half of peak will appear across the load. This is during positive half cycle. Okay, and during negative half cycle, the curve like that will appear. This is negative and this is positive. Hence, point A will be negative and point B will be positive in this circuit. This point is B and this point is B. During negative half cycle, this voltage will appear at point B. That is, point B will be positive and point A will be negative. Hence, the diode will be reverse bias this point will be positive and this is negative, hence the diode will be reverse bias. An ideal diode under reverse bias condition, it behaves like open switch, hence the applied voltage does not reach to the uh, load resistance RL due to the open circuited, and hence during this negative cycle the voltage will be 0. This is during negative half cycle. Hence we get for full cycle we'll get positive. For positive cycle we get positive peak Vm, and for negative cycle we'll get 0 voltage. Since half-wave rectifier only rectify the half of the input AC signal, that's why it is called half-wave rectifier. For next cycle we will get, for positive cycle we will get a positive peak, and for negative cycle we will get again 0, and this will repeating. This is for one cycle T, and this is second cycle, it will be 2T. So we will get this type of rectified output. It is not a pure DC, but it is a pulsating DC. We have unidirectional DC, this 0 to peak and then 0 and then peak then 0. We'll get an average of DC, average voltage, which will be DC. We can take average. Now we can also see when diode is forward bias, for positive cycle, at the same time for negative half cycle diode will be reverse bias. It is important that reverse breakdown voltage rating of diode be high enough to withstand the peak reverse biasing AC voltage. When the diode rating will be such that when it is reverse bias during negative half cycle, it must withstand that reverse voltage, which is the which must be greater than Vm, that is appearing during negative half cycle. And PIV, peak inverse voltage, it is also called PRV, peak inverse voltage. The diode rating must be have high PIV in comparison to Vm. Now we can calculate the efficiency of rectification. By observation we can see only half of the AC cycle is rectified and half of the AC cycle is not rectified. By observation it can be seen that only 50% efficiency of this rectifier is. However, there is in practical or actual rectifier we have some losses, and the theoretical efficiency will be about 50%, and there will be some losses in diode and other circuit components, we can also get less efficiency than 50%. This can be calculated. Now, efficiency of a rectification efficiency. Rectification efficiency. How it can be calculated? Rectification efficiency is defined as any efficiency is output upon input. The output is DC power, input is AC power, and multiplied by 100. This is called rectification efficiency. For this we have to calculate AC power and DC power. PDC equal to, for DC, IDC square into RL, and PAC equal to IRMS square plus RF plus RL. RF is the forward resistance of a diode and RL is the load resistance. Now you have to calculate the DC value of IDC of load current. We can see this is load current IL. We have to calculate the average or DC value of that. Then IDC of load current. For this, we have the wave shape. This is positive half cycle, if we have an AC voltage like this, positive, this is negative, this is positive, and this is negative. This is VI and this is V naught. We can say IL or VL. This is 0, this is pi, this is 2 pi, also 0, this is pi, this is 2 pi, and the T time. So average value, we have a formula. Average value average value equal to area under the curve over a cycle, area under the curve over a cycle upon base. Area under the curve is, this is the area under the curve, and one cycle 0 to 2 pi, one positive and one negative becomes one complete cycle, and under one cycle we have 0 to pi curve, and pi to 2 pi we have 0, but we have base 0 to 2 pi. We can write it I average equal to 1 upon base 2 pi 0 to pi I d theta. We have equation for sinusoidal voltage, Vm sin theta, and for sinusoidal current we have Im sin theta. Then we can write 1 upon 2 pi 0 to pi, I can be written as Im sin theta d theta. We can calculate this. Im can be taken out, Im upon 2 pi, and we can take integration of sin theta is minus cos theta, putting the limit 0 to pi, we can putting the limit Im upon 2 pi, we can put it for pi, it is minus 1, and for 0 it is also minus 1. We can write it, this is plus 1 and this is plus 1, 1 plus 1 is 2, that is Im upon 2 pi into 2, that is I average equal to IDC equal to Im upon pi. We can now PDC equal to IDC square RL equal to Im upon pi square into Rn. Now for AC power, we have to calculate IRMS of load current. IRMS we can define the area under a square of rectified output over a cycle upon a base. We can write 1 upon 2 pi 0 to pi I square d theta under root. This is called root mean square value. We can write like this: IRMS square equal to 1 upon 2 pi 0 to pi I square. We can put Im square sin square theta d theta. Further, we can write Im square upon 2 pi 0 to pi sin square theta d theta. We can write Im square upon 2 pi 0 to pi. We can write sin square theta equal to 1 minus cos 2 theta upon 2 d theta. We can write Im square upon 2 can be taken out, 4 pi 0 to pi 1 minus cos 2 theta d theta. We can take an integral of 1 Im square upon 4 pi integral of 1 will be theta, and we can put it theta and its limit 0 to pi minus integral of cos 2 theta is sin 2 theta upon 2. Can also put its limit 0 to pi. We can solve this. By putting its limit Im square upon 4 pi, we put it by putting its pi value, pi minus sin 2 pi upon 2 minus, you can put by 0 limit, 0 minus sine 0 upon 2 this all become 0 and this will also become 0. Now we have Im square upon 4 pi into pi. Pi and pi will be cancelled out and we have Im square upon 4, hence I RMS equal to under root Im square by 4 equal to Im by 2. This is the RMS value of load current. Now we can calculate AC power. PAC equal to IRMS square RF plus RL. AC power will be equal to the sum of power dissipated in diode and power dissipated in the load. We can write Im square by 4 RF plus RL. Now efficiency can be calculated as Im by pi square RL, Im by 2 square RF plus RL. By solving it, you find it 0.406 upon 1 plus RF upon RL. Since forward resistance is very less than RL, then the ratio of therefore RF by RL is very small as compared to 1 and can be neglected. This can be neglected. Now therefore efficiency can be found as 0.406 per unit or 40.6%. We can see the efficiency of a half-wave rectifier is only 40%. The advantage is it is simple and since only one diode and one transformer is used, it is cheap or it is economical. This what is disadvantage? Disadvantage is it has low efficiency and since it half cycle is 0 and half cycle has pulsating DC, it has high ripple. Okay. Now this is about half-wave rectifier working and its derivation for efficiency.